Okay, let's get started. So last time I start talking about the ADM, um, the mass and so on. But before reviewing that, I will talk about a bit more about this comma integral and Hamilton formulation. Yes. The quick answer to last time, I briefly talked about the linearized version of the Einstein equation, and then try to keep the ADM energy and so on. And I can't answer the question the last time students asked, but before then I'll talk about the comma integral and so on. Okay. So Nether theorem tells us comma integral. So today's we talk about today's plan is comma integral, and also Hamilton formulation. And then ADM, energy or mass, angular momentum. Okay, so that's the plan. Anyway, so if there is something going on, I mean, if time permits, I'll go to black hole dynamics. But I'm not gonna rush. It's as I mentioned, this course I will do a bit slowly than my usual pace. So these are today's topic, and then this one the answer to the last question. Okay, so before that, let's talk about comma integral. So what is the so Nether theorem? So one of the most important theorem in the field theory is Nether theorem. So given a continuous symmetry, then conserve charges, conserve the current actually. In the case of the G, okay. So before going that, for instance, in the case of electromagnetism, so you have the Gauss equation or like Maxwell equation in J mu E. So this is the one of the Maxwell equation, and then here of course is the del mu, J mu is equal to 0, del mu, F mu, and then this is equal to 0. So since this is the antisymmetric, F mu is antisymmetric, so therefore the it's obvious that the current is conserved, and then Q is of course this is a conserved current, and conserved charge is just a integration over spatial time. So this is T, and then sigma some time is constant, T is constant, so T is constant. So then Q is equal to minus gamma N mu J mu. So N mu is the unit vector, also normal to sigma T. So So if you just take a contraction with the, if it is a really, how to say, the Minkowski case, this is NT is just a delta T. In the Minkowski's case, this is the case, and therefore you just pick T component and integrate over the spatial surface, spatial hypersurface, you get the charge Q. So this is we already knew, and then we can manipulate this one, and then mu, like this way. And then just do the integral parts. Integral parts, we can have this one is equal to minus so integral by parts, you have the spatial infinity. You just have a flux of the spatial infinity. This is just what Gauss tells us like almost 200 years ago. Square x, so boundary of sigma. Sigma mu, f mu, like this way. And then, of course, what sigma is that, so you just consider the time t, and then you just consider the spatial infinity. So spatial infinity, it's just schematic. So this is sigma t and then del sigma t, and normal vector is the also normal vector is normal to sigma t, but small sigma here. Sorry, I think you should tell me where I make a mistake. Nu. This small sigma nu vector is the how to say, orthonormal to the boundary surface, the boundary of the sigma t. So therefore, yeah, I mean that's what you learn in the electromagnetism, that the essentially F nu is something like anyway 0 0 0 0. I don't remember the notation. I don't remember which one is plus minus, but anyway, so NT pick the, how to say, the first row or first column, and the E part, and the sigma will pick the which part is also normal to the normal to the boundary surface. So this is Gauss law. Okay, so that's what you learn. And then
here gamma is the determinant of the matrix of spatial part.
yes, spatial part. So gamma is induced metric on sigma. So this gamma is induced metric on sigma. Gamma 2 is induced metric on the boundary. In GR, how do you see the symmetry? A continuous symmetry. So Nether theorem is symmetry is associated to the Killing vector, as we learned. And then we can compute the corresponding to the so the Killing vector. So as you know, this Killing vector is by definition G mu nu is equal to 0. So if you have a Killing vector field, like whatever, so this is a vector field, Killing vector field, C, and then that will just generate the so-called flow. So one parameter for the Fermat prism, and out of which the metric doesn't change. And this is equal to del mu, C mu, del mu, C mu. Okay? And then, so we can easily construct the current as associated with the Killing vector field like this way. So this T mu nu is a stress energy tensor, and then C nu is the Killing vector. And then del mu J mu T is equal to del mu C mu. And then we just do the apply Leibniz rule. And so by conservation of the stress energy density, first time 0, and then since T mu nu is symmetric, T mu nu is symmetric, so therefore the killing vector vector field, this is equal to 0. So therefore one can easily construct the current. And this will be used, will be used for the proof of the first law of the black hole thermodynamics. So this will be used. First law. Okay. So that's the case. And as I mentioned, if you're looking at anyway. Okay, fine. So the other method is the so-called purely use the Killing vectors at the spatial boundary. So that is called common formula or integral. Okay, so that's another method. So this is one method to construct the conserved current, and the other method is to use the spatial the Killing vector at the spatial boundary, but a bit ad hoc. I could introduce another current, which is the contraction of R mu nu and X nu, like this way. So I will introduce another current like this way, and then there is a Killing vector. Yeah. So there is an important formula for Killing vectors. I think, do you want me to derive? So this one is like something like partial nu. It's really non-trivial identity. So this is equal to this one. So this is highly non-trivial identity, which for me took a lot of time to derive it on Scratch. In fact, do you want me to? So this is we have not only this one, not only use this one, but also you have to use. So this step is non-trivial. So you have to use the Killing equation plus n, and then how to say? It's called Bianchi identity. Bianchi identity of curvature tensor R mu nu rho sigma. Do you want me to derive, or it's written in the appendix I wrote? Because I'm pretty sure if I do it again on Scratch, it takes a lot of time, so I just write it down in appendix. Do you want me to derive or not? Okay, but I can just give you some rough sketch of the. So we know that the sketch of this derivation sketch. I'm not gonna write down everything. So it's in the minor. So every day almost I update my lecture notes. So it's better to look at the overleaf updated one. So appendix A.5, I wrote this one. Bianchi identity is something like this one, and then everything becomes cyclic. So. Is equal to 0. Okay, and then so we know that this guy is equal to del nu. Okay. Essentially, this is given by like this way. is the commutator of the covariant derivative. I mean, okay, if you act on this is rho, so you get something like this one, right? Mu sigma c sigma. So like this way. So this is the curvature equation, and this is a first Bianchi identity. And using that, one can show that the totally antisymmetric is equal to 1/6, and R plus R plus R is equal to 0 times B is equal to 0. So this is not only, so this equation, so this is, I should use B actually. I should use B. So it's not Killing vector. It's not necessarily Killing vector. This equation is hold in the any how to say, any vector. So this is totally antisymmetric. So this is totally antisymmetric. Remember, is equal to 0. And then you can just do manipulation on left hand side. Do a lot of manipulation by using this Killing equation. So I'm not gonna write down indices. It's a kind of messy, so that and then use this Killing equation. Apply this Killing equation many times on here in left hand side. Okay. So left hand side, if you apply this one many times, at the end of the day you will get the following equation. So this is 2 times del nu c rho plus, okay, so first of all, let's first insert this b in c. So replace this b by c in Killing equation. That's totally fine. And apply the Killing equation many times. And what you end up with as follows. Like this way. Is equal to 0. Is equal to 0. And then if you use this one, what you get is that the del nu c rho is equal to R rho mu alpha c alpha. So that's what you get from this equation. Essentially, it will give you curvature tensor, and you use the symmetry of curvature tensor, you get this. Okay, then you just take a contraction mu and rho. So if you take contraction mu and rho, is it the what I wrote here? Yeah. I think the index is opposite, but it's okay. What you get is that the R contraction with mu and rho. So nu alpha c alpha. So that's the derivation. It's kind of so this step, if you want to know about the detail, I already write down the detail, how to say, transformation rule in a lecture note. So, so you can just follow the appendix. But anyway, so that's the derivation, and then so you get this one. So this is the case. Okay. So you can easily see, any question? So anyway, so you can easily see this will also conserve. So I just the last time I used T, but I can use R to define a conserved current. This is the case. And this is equal to 0, because again, this is symmetric. But if you use a symmetric mu nu, so you get the symmetric mu nu, you get 0. Okay. So this is conserved current. So this is another way to do construct the conserved current. And what's nice about it is that now here you just have a derivative. So here it's just the derivative of Killing spinor. So therefore, again, we can just define E is equal to appropriate normalized quantity 4 pi g, and then spatial surface gamma, and then and mu. Okay, so this is so I just so this is equal to J mu to define the energy. So it's called common energy, or whatever called energy, and they do the integral by parts again. So by integral by parts, you get the sigma. Okay, like this way. And then this is again only use the killing spinor, and then you just again the sigma is here and the boundary sigma is here. Okay, boundary sigma is here, and then you just do the the integral over the boundary of the surface. Okay, so that's called a comma integral, comma formula, and so on. So this is purely used the Killing spinor at the boundary. Okay. So that's the how you define the conserved quantity, conserved energy at the boundary. In the when you have a killing spinor. Okay. But energy and Hamilton, or Hamilton is a much more general object.
Here we will cover a derivative, right?
This one?
No, G mu, G R mu.
G R.
The first, the last line.
This one?
Yes.
Yeah, it's covariant derivative.
How it is symmetric?
So this is equal to 1/2 dou mu dou mu C mu plus dou mu C mu is equal to 0, right? It's totally fine, right? So this can commute, right?
How is this? The problem is how is this commute? Because this covariant derivative is not commutative. That's why we have Riemann transform.
No, it's just or
If it is partial derivative, then it's okay.
it's a partial derivative. It's
Partial derivatives are commutative.
that's true, but it should be because I mean if you only look at this one, this one is also conserved, right? R mu nu is symmetric, right? And then dou mu R mu nu is equal to also 0, right? If you use the conservation of the stress energy tensor. So this is equal to del mu. What was that? T mu nu minus 1/2 G mu nu T, right? So this is equal to 0, right? So if you can ask this one, and if you ask on this one, this is 0, this is ask on this one is also 0. It's totally fine. But this derivation may be wrong. Wait. Yeah, maybe this derivation is not, but it should be 0. Anyway, so if you use this one, this is equal to 0, so you can show. Okay. Maybe my explanation is not correct. Is equal to 0. But anyway, this is equal to 0. Okay. And then, okay, so for instance, example. Short black hole, space-time.
Why covariant derivative of a scalar is 0?
I'm sorry?
Covariant derivative of t is 0, right?
Oh,
No,
right. This is equal to what?
And this gives you partial derivative here because the first part is minus configuration of number. So the second part is like derivative of scalar, right? This is a partial derivative. No, t is scalar. That's why the covariant
That's fine.
derivative means partial derivative.
Okay.
So then we have partial derivative instead of covariant. So we have this means everything.
Good question. I didn't think about it. Oh, it should be 0. How do you... Does anybody found how do you show that this is equal to 0? Yeah. No, I think it should be contract with C, right? Oh, okay. I think we should contract with Xi nu, right? Xi nu. And then this should be contract with Xi nu, right?
Lower index.
A lower index, okay, lower index. Xi nu, right? And then, so this is okay. This will keep you right? And this will give you C nu, del mu t, right? This del mu t, right? And then, since it's killing spinner, this should be 0. Sorry, this is new. So since this is a killing spinner, this should be 0. I think that's how it should be 0. This should be. How to show that the killing spinner? If it is 0. I mean, if it is not 0, definitely it's not killing spinner. Well, how to show that? This should be 0, right? How do I show this one? There must be a way to show this one by using Einstein equation. Oh, okay. So R mu nu. Okay, sorry. Let me do it again. Del mu J mu R is equal to del mu R mu nu sigma nu. Okay, and then so the second part is obvious. So therefore this is del nu partial mu R mu nu, like this way, right? And then this should be 0, but for killing spinner, I don't know how to derive that. Sorry, I don't know how to derive. Then can anybody derive this one?
Someone posted as derivation in the WeChat group.
Oh, someone post? Thank you very much. Okay. The second term is the so do you use the so what's written is that this is equal to 1/2 del alpha R G alpha whatever beta. Is it like this way? Well, why is that? Is it just vacuum Einstein equation?
No. Because of the how do they
So how do you derive this one? And this is equal to
because the contraction of the
derivative of the Einstein tensor is there.
Okay. Okay, let's accept that. So this is C alpha the alpha R. Okay? And this is equal to 0?
Yes. Because of this is Killing vector.
Killing vector.
And for the adopted coordinate system, they do not have the,
Yeah, they
coordinate, the Killing vector parameters coordinate, so it might be the.
Yeah. So we can take the derivative. I mean, yeah, I think this should. Anyway, so they should be equal to 0. Because I mean, so if you have a Killing vector, so let's say a Killing vector, you can always find a local coordinate such that this one has some coordinate t, whatever, t or x or whatever called t 0 0 0, like this way. And the metric is independent of t. You can just independent of t. Easy, independent of t. So independent of t. So metric always can be chosen locally that such that you can find a coordinate such that the metric is always independent of t. So therefore, the c mu acts on the this quantity should be 0. I think that's true. That's true, but I don't know how to derive. Anyway, so this step, are you guys obvious? I'm not obvious.
Yeah, for example, the covariant derivative of Einstein tensor is 0, right?
Uh-huh,
And
yeah.
this is just from this equation. We take the
Oh, I
covariant
see. Covariant derivative of this t mu nu is equal to g mu nu, right?
Yeah,
Some number. Yeah. Okay. So then this is okay, and this is good. Okay. Good. Thank you very much. Thanks for the help. Okay. Fine. Okay. So that's the derivation. How this one is okay. Okay. So I think I should write down the lecture note. Next time I will teach this one. I will again stumble on the unless stumble. Okay, so let's do the some example to derive what was that? Which one? Oh, this guy. This guy. Okay. Fine. So for short and 0 is my how to say? So you can just have so we know that the n is a time-like. Okay, short, as I mentioned, so partial t, this is the Killing vector. Okay, Killing vector. And then normal, as a normal vector, so one can have the, you can choose like the orthonormal like this way, so that the and mu is something like 1 minus 2g. I don't know why I put the g, but anyway, so 1/2 and 0 0 0. So one can have this coordinate. And for sigma, it's the again. So sigma is the can be just considered as the radial one, partial r. So sigma can be sigma mu can be understood as partial r mu. So therefore, this can be understood as 0. 1 minus 2gm over r minus 1/2 and then 0 0. Okay, like this. Okay. And then this is a Killing vector. Sorry. This is a Killing vector. Okay, so if you consider, so we try to evaluate this quantity at the boundary, this quantity. So we try to evaluate this quantity. And then, so this is equal to minus del 0 c del 0. Mu is equal to 0. And xc equal to nu equal to 1. Okay? So this is the case. And if you evaluate this one, so I just write down the lengthy derivation for this one. Del 0 c1 plus gamma, sorry, c1 and 1 0 lambda 0 1 c1 like this way. No, sorry, so c0 and 0, sorry. This is a non-trivial part, and this is the non-trivial part only come from this one. Okay, and then, and this is equal to minus 2gm over r square because of this gamma 100. Gamma 100. Gamma 100. So actually G00 and C0 will cancel each other. Yeah. And this is equal to, and if you just integrate over E is equal to 1 over 2 pi G, and appropriately normalize the measure d phi and r squared sine theta gm r squared, and we know that at the how to say special infinity the area is 4 pi r squared. 4 pi r squared. That's the area of sphere, and this is equal to m, and this is equal to m if you integrate over. So this one cancel and this one cancel, and if you integrate over this one, this will give you 4 pi r squared, and this is r squared cancel with this guy, and then you get the m. So that's the derivation. Okay, so that's the case. So this is a short shell. And one can also do the same computation. In fact, in the case of the what was that? Car. So the another important killing factor is the del phi. So this is also killing. So therefore, if you use this comma integral, one can also define the angular momentum as a conserved quantity.
This is energy of black hole, right?
Yes.
It's just equals to its mass.
It's mass, yeah. So that's how we normalize this part actually.
Okay. I mean, is it true when it is black hole also? The energy is just equals to
Yeah, it's the same. They just give it that. Okay, but I mean, if it is non-stationary, non-stationary means del T is not killing vector. It's not killing vector. So therefore, so one cannot define energy, but it's still there is a Hamiltonian. There must exist a Hamiltonian in the field theory. So okay. So this one is the construct by ADM. Arnowitz, Desson, and Missner. Okay. Arnowitz. Missner, yeah, so that's the case. So this one is so Hamiltonian formulation of the GR is given by this ADM, and this will give you by the following decomposition. So 3 plus 1. Oh. So to do that, so we just considered some current, timeline current T, and then you just consider the following hypersurface sigma T, and then whatever sigma T plus delta T. And then so here you have a tangent vector of T. So this is del T. And it's decomposed the normal vector of this one. This is n and mu and I, like this. Like this way. So you just decompose. This is the so del T is n small n mu plus n I. So this is the also normal to sigma, and then this is the other orthonormal basis, spatial orthonormal basis, spatial orthonormal basis. It's not orthonormal, it's normal basis is better. I think it should be, yeah, normal function. No, it's not ortho. Normal. Okay. Spatial basis is okay. Spatial basis. Spatial vector. Spatial vector. Then the metric can be written as follows. So ds curl qij, and then dxi plus ni dt times dxj plus nj dt, like this way. And then so we just decompose. So this is the so here this is called somehow it's called lapse function. And then this is called shift function. So these are called shift function somehow. And the Qij is the metric induced on the so the Qij is the somehow the induced on the G, how to say, G mu nu plus N mu and nu times the, how to say, I mu del J. So that's the case. Maybe I should write down like this. Ni. So that's the. So this is a induced. How to say? So this is the induced metric on the induced metric on sigma. So as I mentioned, so I mean this is familiar, right? So if you have a hypersurface, and if you have normal vector and mu, so in this matrix here is always like a g mu nu plus n mu n mu. So this is the what we learned, and then for instance, I mean if you consider t mu nu for a rho, I would say g mu nu plus u nu plus p g mu nu plus u nu. So this is the ideal gas. Ideal how to say gas of a stress energy tensor of the perfect fluid. Okay, and when you consider rho is the really u is the time unit vector, and the g mu nu and the u mu nu. So this is the induced metric on space time. Okay, induced metric on space hypersurface. So this is exactly the same as here. So this is the induced metric. Okay. And then we just write down the Einstein equation in this variable. And then you just move from Lagrangian to Hamiltonian. So that's what we are doing. So what we learned in the classical mechanics, L is so L in Hamiltonian is a given by. L is a function of x and x dot, and to do the Hamiltonian is p and q, p and x, and you have to do is x dot minus L, so like this way, and x and then t, like this way. So that's what we need to do. So similar thing we need to do for the Einstein equation. Okay, so to do that, so what we need to think is that this Qij is the Qij corresponding. So in the Qij is corresponding to this guy, and this is given by and then. This one corresponds to Qij, and this one is I call it pi ij, which is the conjugate of Q. It's defined as the derivative of L divided by Qij dot. So that's how I define the in space time. So this is the metric on sigma, and here it's a conjugate variable here. So to do that, we have to write down Lagrangian in terms of Qij and double dot. No, it's not dot. Yeah. Okay. So then action is given by S. If action is given by what was that? So R. So the Lagrangian is given by R, right? Lagrangian is given by R, and this can be decomposed as follows. So Einstein tensor R can be decomposed three-dimensional Ricci tensor plus epsilon KAB and KAB minus K squared plus 2 ERAB, and then NAB, NB. Okay. So this is a four-dimensional Ricci scalar, 4D Ricci scalar, and this is 3D Ricci. And then, so this is the extrinsic curvature. So this is the extrinsic curvature. On sigma. and the K is the contraction. QAB, KAB. Okay. So those are the Ricci scalar can be decomposed into the following way. So just to remind you what is the extreme curvature. So last time my explanation of the extreme curvature is not that good. So I just remind you that what the extreme curvature is. That
What you mean by 3D Ricci scalar here?
I mean use this metric QAB to compute the three-dimensional Ricci scalar. So in this metric on sigma is QAB, right? Q. This is I call it the Q mu nu or whatever Q mu nu. And then you can compute the induced Ricci scalar and using this induced metric. Okay, and then after some manipulation, one can just so here. Okay, so let me recall what is the extreme curvature. So because I mean last time, so extreme curvature of the hypersurface is the I think so this is sigma, and then extreme curvature is something like the difference between so it just consists normal vector and mu and mu, something like this one, and mu. And you just do the power transfer of this, the power transfer also normal one to here. Then if you do the power transfer also normal one is like this way. So this is power transport. And the difference between tau and mu is given by the this extrinsic curvature. Is extrinsic curvature, so that the K mu nu is equal to tau mu and then n mu, like this. So this is the here n has to be also normal. To the so and K mu nu is purely symmetric, actually symmetric under mu and nu, and then since there is no rotation, and also K mu and n nu is equal to 0, K mu nu, like this way, and then moreover, so K mu nu can be understood as the Lieb derivative of n of the induced metric Q mu nu. So that's the extreme curvature. And then the last time when I talk about the Ricciardo equation, so we just have this Q mu nu, K is equal to Q mu nu, K mu nu is equal to theta. So that's what we learned last time. And here, so what we are going to do is this. So this is a Lagrangian of the. So when you consider Einstein-Hilbert action, R is a Lagrangian. R is a Lagrangian. So that, but we have to write down Lagrangian with respect to Q and Q dot. Q and Q dot. So now Q is the dynamical variable. Is a metric is a dynamical variable in this case. And then we just decompose it, so the four-dimensional curvature in terms of like this way. So therefore, so K is written Q, and also K square is written Q. And here you have to be careful a little bit about how to treat them. So when you do this, so here, so and mu is just do the parallel transpose to compare. So this parallel transpose direction is also given by whatever derivative. maybe I should use nu here. But anyway, so okay, x new direction. So therefore, this del, how to say it, del and mu is also should depend on mu and nu. Okay, so that's why you have a two indices. Okay. And then bit of manipulation you have to do for the last term. Bit of manipulation you have to do last term. So this time, to see more clearly about the Lagrangian. So this one is, so if you try to do the manipulation of the last term, so I just write down the manipulation how to do that. And A and B, and this can be just written in the it's a very I just write down that I'm not gonna do all the calculation. It's written 3.134 in the lecture note. Can be written as follows. Everything written in terms of the derivative of n and the extrinsic curvature minus NB del A and A and minus KAB like this way. So therefore, the action of the action is given by like this way. So B is the four-dimensional space-time D for x. So this is the Einstein-Hilbert action, and of course the cosmological constant is equal to 0. And then here we can just write down the following: the Bach term, KNE, KAB, and then minus k squared, the n square root q d for x, and there is, since the, so if you just consider, so where was it? Yeah. So here I use the combination of this guy. This guy is written in here, and so the combination of this part and this part will give you these. Okay, so combination of this guy and then this guy. And what's left is the total derivative. So therefore, this will give you boundary. So this will give boundary term, which is something like this way: del V, and then del A and B minus n B, del A, and it's d of sigma B. Okay. So that's the action, and it's, for time being, we just leave this term as it is. So we just consider this one is the at the infinity, this is the somehow fixed. So I mean, a boundary integral do not contribute for time being. So therefore, if you only look at the Bach one, so this is the Bach. People call Bach and the boundary term. If you consider only Bach term, so the Lagrangian can be understood as 60 pi g Lagrangian can be understood as the, say, okay. I mean, Okay, so 16 pi g Lagrange of dt can be understood as n and then R3, three-dimensional rigid scalar KAB and KAB, and then minus k squared and square q d4. So that's the case.
Where is boundary term?
So we will consider boundary term later. Boundary term. So let's first focus on Bach. So Bach term. Okay, now so we need to find a conjugate variable. So now we need to find a conjugate variable here. To find a conjugate variable, what we need to do is that we need to explicitly write down this extreme curvature part. Extreme curvature part is this guy given by here, and then we can just manipulate this extreme curvature part. Okay, and this one, so we know that the n and mu is equal to del t. So I already erased. Del t a is equal to n times na plus capital Na. Okay, nj or whatever. Okay, so that's what we know. So therefore, Na can be understood as an inverse of del t of a minus Na. So it's just manipulation. Anyway, so it's a boring, but you have to do. It's a boring, it's tedious, but you have to do. So n is a lapse function, Na is a shift function, and then like this way. And you just plug into here. So the plug into here, what you get is 2n Lie derivative of del t and QAB, Q mu nu, minus L capital N Q mu nu. Okay. And if you write down the following way, you have 2n and the Q dot AB minus dA and B minus dB and A. And then this is a covariant derivative. So these are a covariant derivative with respect to in how to say, it's the on the hypersurface sigma on hypersurface. Okay, so that's what I used for the. So this is just a, some kind of like a usual Lie derivative acts on G mean. So now, so this, if you look at the extreme curvature, it has the time derivative of the spatial metric Q. Okay. Okay. So therefore, you can find time. So these contain Q dot whatever AB and so on. Okay. So then one can find just a canonical conjugate variable for Q, which is pi ij as follows. Equal to, sorry. So first of all, pi ij is like a del Lagrangian del Q dot ij, and this is equal to somehow 1/16 pi g, which is some normalization of the action here, and times how to say, n square root q del q dot ij, and then k whatever ab k minus k square. Okay, and then this is equal to square root q k ij minus q ij k. That's what we used. So here we use the fact that the kij is contain q dot ab, and the k here is just contraction of qab kab square. So I use this fact to derive this. So this is a conjugate variable. So now, so what we did is that so it's a tedious manipulation. So what we did is as follows. So we just decompose the space-time, 4D space-time into 3 plus 1 dimension. Okay, 3 plus 1 decomposition, 3 plus 1, and this is the parameter and mu, and this is parameter and I, so that function. And this is first step, and second step, write down r or whatever 16 pi r or whatever 16 pi r g r in terms of QAB and then KAB. Okay, KAB. Okay, and the boundary term. Boundary term, which is given by this NA, derivative of NA. And number 3 is a define. Number 3 is a find. The find. Number 3 is a find. Treat QAB is a dynamical variable. And find the conjugate, canonical conjugate to pi ij variable to q or q pi ab qab. That's what we did. So now we can define the Hamiltonian by just ordinary way, some proper normalization, and then pi ab and the q dot ab minus Lagrangian times 16 pi g. We're gonna okay, like this. Okay. So Lagrangian is written here already. Lagrangian is given here with the appropriately, So Lagrangian is given here as the spatial integral. And then, so we know pi ab is given over there, and the q dot is here. Okay, and then that will give you as follows. Okay, where is it? Okay, and we have to use the following fact, of course, q dot KAB is equal to, so I have to write down the q dot and the KAB is can be written vice versa. What was that? Where is it? 2n q dot AB minus DA and B minus dB and A. So therefore, so q dot and then KAB is can be just translated into the extrinsic curvature here at the cost of these derivatives. Okay, so after lots of manipulation, which I already did, And this can be written as follows. So I already wrote, I'm not going to write down everything, but this can be understood as the square root q, the n times this minus 3-dimensional scalar curvature plus KAB minus k square, and then okay, let me write down here, plus minus 2 square root q n j nj and sorry di kij minus qij. Okay. Okay. Anyway, I and j are just spatial indices. Anyway, I, j, and spatial indices. And then plus some total derivative. Plus 2 di plus total derivative 2 di square root q kij minus qij n and nj times nj, like this. Okay, so those are Hamiltonian of this one. And again, we only focus on back term. If you only focus on back term, so this can be written. If you only focus on back term, so we can just write down the following Hamiltonian. Hamiltonian can be repackaged into here, like this. Yeah, actually, this is kind of like a cheating. I'm kind of cheating here. Here I somehow missed the integral of the, what was it? Yeah, square root q d cube x. So I use, in my lecture note, this part is missing actually. In my lecture note, this is missing. Because I mean here, did I erase? So L is the, sorry, L dt is given by this integral. So dt part is the, if you ignore dt part, special integral is left. Here, special integral left for L. So, yeah, I think L contains special integral, so maybe something should be here. Anyway, special integral has to be written here, nice way. And then, so what we get is 16 pi g is a normalization, and the Hamiltonian is given by minus nh plus 2ni hi such that the h is equal to 3, which is scalar plus k square minus kij, and then hi is equal to dj kij minus qij and k. Okay. So those are back terms. So here we ignore all the boundary terms at this moment, and then these are the this become a Hamiltonian of the Hamiltonian of this how to say this 3+1 decomposition. And here we treat the how to say q and the pi or k. Qij or Piij or equivalently Kij are the canonical conjugate variable and dynamical variable, but it's not the n and so this lapse function and the shift function are not treated as a dynamical variable. So here we can consider this n and I can be understood as some kind of like a Lagrangian multiplier. It's not Lagrangian multiplier. So since it's not a dynamical variable, so therefore, I mean, as always the Lagrangian multiplier does, constraints is this is equal to 0, this is I equal to 0. So this so Hamiltonian, so this is called Hamiltonian constraint. Hamiltonian constraint. And this is momentum constraint. We'll give you the Kali H. This Kali H, I call it Kali H. And the Kali H hat, Hi should vanish. So consequently, this will give you the total Hamiltonian is equal to 0 somehow, from the bulk analysis. And in fact, if you solve this Einstein equations for vacuum, you will get these equations. So these equations can be also obtained. So these equations can be obtained by vacuum Einstein equation. Okay. So if you only look at the back part, somehow Hamiltonian of the GR looks to be 0, but this is not the correct analysis because we just all ignore this boundary term, these boundary term and these boundary term. Okay. And then I think I would take a break from now and include the boundary, boundary term to get the correct Hamiltonian. From now, from after the break. So the point is that if you only look at the back term, Hamiltonian looks like 0. So because that's what I want to say. And from now on, let's take a break, and then after the break, I will give you the correct analysis, including boundary term. Okay. So let's take a break.
This gives this.
Huh?
For example, from this equation, you get this, right?
Yeah.
How? If you take the derivatives.
So this will keep boundary term. So I just ignore boundary term.
You just ignore it.
Yeah.
Okay.
And I only look at the bulk term.
The next step is to include this term.
Yeah,
as
boundary
well.
term. Yes. Okay, and shall we resume in that case? Okay, so far what we did is the this step. So 1, 2, 3, and then write down the Hamiltonian, and Hamiltonian is given by here. But if you use this Hamiltonian, the Hamiltonian automatically 0 because n and I will give you Hamiltonian and the momentum constraint, and then that will automatically give you Hamiltonian equal to 0. But as I mentioned, the what's wrong with that we just ignore boundary term. So this term is important. This term is important for energy. This term is important for energy. And then here, this part also important for momentum. So important for momentum. So I ignore this part. Also, this part I ignore. I only consider the first and second term in the Lagrange Hamiltonian over there. First and second term in Hamiltonian here. But this term is also important, and this term is important. So let's do the analysis again, including boundary term. Okay. So it's a tedious. So this means that the important thing is that somehow in the system, so Hamiltonian and the momentum can be measured only at boundary. So important lesson we learn. So because since if you only look at the Bach term, the Hamiltonian is always 0. Okay, Hamiltonian is always 0. So to measure the energy and so on, so you have to really go to boundary. So that's what we learned from this analysis. And then, so to include boundaries, so what we need is that we need to include so-called Gibbons-Hawking term. So do you want me to? So I'm not gonna derive everything about everything, because I mean we already did enough like a lengthy, tedious calculation, and most of you guys get bored. So I'm not gonna derive everything. But to have the system with the boundaries, Einstein action should be modified. So space-time with boundary. The Einstein action can be modified as follows: 16 pi. Oh, sorry. G B r minus 2 lambda square G D minus G. Like this. Okay. So this epsilon is just the normal. So n square, n mu is equal to epsilon. Is epsilon. So we consider the space-time B with boundary. So this is whatever B is the 4-dimensional space, and the boundary B is the 3-dimension, and the n is a normal, orthonormal vector, and mu. and then whose the norm is in fact epsilon. And then at the boundary we have to include this one. So this is called Gibbons-Hawking term. Hawking term. Hawking term. And then here this is called external curvature. So this is external curvature, normal external curvature. So this is really invariant on the source. If you just do that, del S del H mu nu. So here usually we only look at the bulk term, and at the boundary delta H mu nu is equal to 0. Well, the G mu nu or whatever. Del G mu nu is equal to 0 at the boundary, usually, to derive the Einstein equation. But if you assume that the del G mu nu is non-zero at the boundary, so you have to include this one, because to cancel boundary term. And then this one, derivation is, I wrote appendix C in the lecture note, so I'm not gonna do the derivation of this one. So I will accept this one and move on. Yeah. So otherwise it's going to be kind of again lengthy calculation that makes it bored. So let's accept this one and compute everything including the boundary one. Okay.
So usually delta G mu nu is equal to 0, right? This is what we usually do. But what does this physically mean if it's not 0? Interpretation.
So if you have a boundary and the delta G mu nu, I mean in boundary, you can still change the metric, right? You can still change the metric. So usually you just assume that to derive the Einstein equation, roughly speaking, delta S is equal to G mu nu, and then delta G mu nu, and it's some constant, and then square root minus G dx, plus the total derivative of something, and then square root minus G d for it. And this is del G and blah 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 blah. Okay, del G and so on. And here, usually we ignore this boundary term because delta G at the boundary is equal to 0. Okay, but we can still consider that delta G is non-zero at the boundary.
So what is the interpretation of this?
It's totally fine to change the metric, right, at the boundary. If you have some space-time with the boundary, it's totally fine, right? Okay. And to cancel this term, so we need to add this Gibbons-Hawking term, and then that is written in the appendix of C. So, but I'm not going to derive that. Okay. So where are we? What are you trying to do? Okay. Okay. To do that, we consider the following spacetime. So if you consider the following hypersum is sigma 1 and sigma 2, and then I call it this one is a boundary, and here sigma t, and then here is st. So we consider this guy is the t, and then x1, x2 3 direction. And the space-time is the following structure. So there is a time translation of hypersurface sigma 1 to sigma 2 by time translation. Sigma t is t is constant surface, and B is a boundary. So this is the really time-like hypersurface. So this sigma 1 and sigma 2 are like a sigma are space-like hypersurface, whereas the B is the time-like hypersurface. So we assume this one, the action is become by using this 3+1 decomposition. Action will decomposition, and then action will become as follows. So I don't think okay. Let me try to write down. S is equal to 1/16 pi g. I'm not gonna write down everything. I mean, it's going to be horrendous. 3r plus k ab minus k square n square q as we saw dqx, and then there's a boundary term like here, which is minus 1/pi g del a and b and k, like this way, and the sigma of b. Okay, so this is coming from here, and then you need to add the so-called gibbon Hawking term, which is as follows. What was it? Minus 1/. Like this way. Like this way. So this one, this term is really this term. I mean, k is the trace of the extrinsic curvature. It's really coming from here. And then given the Hawking term, so that this part corresponding to this part, and then this part corresponding to this part, and whatever. I mean, it's hard to draw. I mean, this B part is the last one. And the k tilde has to be defined appropriately. Where should I write? Actually, it's kind of okay. Maybe I should. So this k tilde is the extrinsic curvature induced on this time-like hypersurface. So this k tilde is defined as the q tilde AB del A RB. Okay. So now, so if you look at this one, the induced hypersurface, the normal vector is really R component. So this R, delta R. Okay. So therefore, if you try to, so this is RA, I call it RA. So if you look at the normal vector along this time-like hypersurface, you have to define like this way. Q tilde AB is again AB is GAB minus RA RB. Okay. So that's the induced metric on time-like hypersurface. Okay, so that's the case. So you have to be careful about the sign here. So usually hypersurface, if it is space like G induced matrix is plus NA and B. So this is plus. But for time like hypersurface, you have to use minus sign. So usually it's like this. So where epsilon is the u. So depending on the normal vector is the space-like or time-like, the sign will change here. Okay, so this is k tilde. Fine, it's a really tedious calculation, but now miraculously, so here, so if you only look at this one and try to define the Hamiltonian, we know that the Hamiltonian, so these bulk terms do not contribute, and then the boundary term we will consider later. And here, if you do the manipulation second term, this term and then these terms cancel actually. These three terms cancel, and at the cost is the very small term. So the second, let's focus on second term. Let's focus on second term. This is the boundary of B. Okay, everything boundary. The boundary of B is the NA, del A. Like this way. Okay, A is equal to minus K d sigma 2 plus sigma 1 K d sigma 1, and then minus B and A and B, nabla A, and then del RB. Okay, so this is the so essentially, so what we need to do is that the here, so the contribution on the space-like hypersurface contribution really coming from here. The second term, it's coming from second term, and whereas the space-time we really see this one. So that's why. So del A, del B, okay. Del A, RB is really coming from here, here, and the NA and the B is just is coming from is the normal to the surface. So therefore, so if you compare between second term and then third and fourth, they cancel. They cancel. At the cost is that the last one. So the only look at what we need to do is the last one. And then, so where should I go? So this is a really tedious calculation. So at the end, what you have is that the at the end, what we have is that follows. S is equal to 1/16 pi g, and then okay, 3 r minus k plus kb minus k square, and square q and the x4. And then here have a boundary term pi g and b. B del b. Like this way. Okay. So here we have the okay. So the cancellation of this second term to third and fourth term, and the last one is given in this way, in this way, in this way. So therefore, this part is really coming from this one or this one. But at the this one will give you this one. Okay, so that's what's really happening. Fine. Okay. And we do the same procedure of the, so this is the action, and here, from here you just define a Hamiltonian. Hamiltonian. Okay, Hamiltonian from here. It's the same procedure, so they just use the same procedure, and what you get is as follows. So I'm not gonna write down everything. So here, what we have is 16 pi gh. The same procedure is the whatever. Yeah. The same procedure. I'm not gonna write down everything. So this b is equal to and h. So this is Bach term, as I mentioned, and I, hi, and square root q, d cube x. So this is a Bach term, and the most important boundary term is minus 2 times st. St is really coming, is this one. Here now also there's a Hamiltonian, so you have to, how to say, really define Hamiltonian on the spatial surface, okay? It's sigma t. So this is the bulk of, so this is the bulk of sigma. So this is sigma t. Sigma t, sigma t. Now, so we need to consider bulk term like this way. So bulk, no, it's not bulk, boundary term. So boundary is st, and I call it, this one is k. So I call it, this one is k. This entire quantity as k, as a k. And then here k, k, I mean appropriately normalized one, so this is normalization times n ds plus 2 times st, and then k ij, kij minus qij, k, and then j and dsi. Okay, so that's okay. And then the last time, so last time is really coming from here. So the boundary term of the previous, the boundary term we previously ignored. Okay, so we know that this guy. Oh, where was? Oh yeah. So here, this guy is really corresponds to this guy. Okay, that's we know. But we in the previous time we ignore a boundary, but we need to appropriately store this one, a boundary term like here. And then in addition to that, we just include this k part into the Hamiltonian. So this is the ADM Hamiltonian. It's called ADM Hamiltonian.
What is k0 here?
So you have to appropriately normalize, otherwise you get infinity. So you need some appropriate normalization for this k, the scalar quantity. So this is normalization. So this is the how to say? It's called, to kill the divergence, what is it called? It's cut off. It's cut off or parameter or normalization parameter. Parameters to avoid divergence. to avoid divergence. Okay. Okay, so the finally I got this divergence. How to say? I got a Hamiltonian, and we know that this term does not contribute the Hamiltonian. So the back term does not contribute the Hamiltonian, and what we need to look at is this boundary term. So that's the derivation of ADM energy of this from 3+1 decomposition. It's really lengthy, but one has to really do the calculation. Any question at this moment? Okay. And as we will see, is that the first time we will give you so-called ADM mass or energy. The second time we will give you is responsible for the angular momentum. Angular momentum. Okay. So let's do the calculation in the Schwarzschild case. Schwarzschild or the curl is also okay. Curl is also okay. I can do the curl too. Okay, let me do the calculation. For instance, what we have is that let's see, what should I do? Let's consider the following metric, Qij. Dxi, dxj. It takes the form of the what was that? The following way, QRR, dr square, and then dr square, and then 2QRA dr dxa plus QAB dxa dxb. So we just write down the special metric like this way, and then we perturb at the infinity. We just do the linear approximation. So at the infinity, r goes to infinity. So this is the so here it's you just use r coordinate, radius coordinate, and then here it's more like a spherical. These are spherical coordinate. Okay. And then R goes to infinity, you have a linearization. What's HRR dr squared plus 2 HRA dxa. And then dxa. Okay, like this way. dxb. So this is a linearization. So if you go to the, if you take h is very small, this will become just ordinary, how to say, spherical coordinate of the Euclidean space, three-dimensional Euclidean space. So HRR is the order of 1 over R, and also HRA is also order of 1 over R. Okay, and HAB, I mean HAB can be taken to be 0 actually. Order of R0 or at most R1, but I mean HAB do not make any contribution so much. I mean it's up to, okay, R is okay, but okay. So then, if you write down this RA is in fact like this way: 1 minus HRR over 2 divided by partial R of A. So as I mentioned, so here we have the constant time sigma t, and the boundary is d, and then normal vector is del R. Okay, like this way. Sorry, not delta R. R. A. Like this. Is R. I call it. And it can be taken like this way. And the K is the. So K is the dA and the RA, like this way. And if you do the computation, what you get is as follows: is in fact is given by 2 over R minus 1 over R HRR plus 1 over R cubed sigma AB HAB, and then plus 1 over 2R squared sigma AB partial R HAB. Okay, so that's the case. And then if you just do the appropriately integral, let's see. So this is the case, and then so the Hamiltonian therefore given by 1 over. Where did I write? Yeah, 16 pi G and ds, and then 2 over R HRR plus 2 over R cube sigma AB HAB minus R squared sigma AB and R HA. Okay, so that's the how you obtain the calculation of the. So this is called ADM. So as I mentioned, so you have to appropriately normalize this vector k, so that I just ignore this part. I just ignore this part. So appropriately, so that is the k0. So that's the k0 part as he asked. So you really need to avoid divergence. You have to really normalize this part, and then just only look at the less than the part to get the correct contribution. Okay, so that's the case. Okay. That's the case. And
AD runs for theta and phi only, right?
theta and phi, yes. Theta and phi. And yes. Okay, and then let's compare with what we did last time. So last time, what we did is that it's very showed a naive computation of the ADM mass last time. Okay, so finally we compared what we did last time. Finally compare with what we did last time. So what we did is just really consider so last time I give the very rough derivation of this guy. So we decompose G mu nu is the very small perturbation at the infinity, 8 mu nu plus H mu nu, and then H mu nu is the order of, is something like the order of 1 over r, and then just write down the linearized Einstein equation, which is the following thing: H mu nu plus dou mu nu. Okay, so I'm not gonna write down all the indices, but it's written in the lectional, so but I'm not gonna write down everything. Minus 1/2 eta mu nu and t. Okay. Finally, I can erase this part. And using assumption T0i is equal to Tij is equal to del T, H mu nu is very small, it's 0, and this linearized equation can be understood as del I del J Hij minus del I Hjj is equal to 16 pi g, and then T00. So that's what we derived, what we did this one. And to define the energy, so we just integrate over E is equal to d cube x T00 is equal to 16 pi g d cube x, and then del I. And infinity and dsi. So by integral parts, we get like this way: Hij minus del I Hjj. Okay, like this way. So that's what we did. And the question is so what he asked is that if you consider the vacuum Einstein equation, this T00 is really 0. So that's what he asked. So T00 is really 0 for vacuum Einstein equation. That's true, but so here at the end the integral is in fact is the boundary. Okay, at the boundary, and we don't know what's happening inside. As we know, so the Birkhoff theorem tells us Birkhoff theorem tells us that if you assume spherical symmetric, okay, spherical symmetric and then stationary, we know at the stationary, and then we know the metric is asymptotically the Schwarzschild. So we don't know, we don't need to know about what's inside. So we cannot distinguish at the boundary. We cannot distinguish what's happening inside. So let's consider boundary, or let's go S infinity. The boundary, you can have like the horizon, maybe short to the case of horizon and the singularity, like this. This is total vacuum, but the Barkov theorem that we cannot distinguish between this how to say, the at the infinity, you cannot distinguish this configuration or the how to say, there may be some sphere, no star inside. Barkov theorem tells us there is a two configuration S infinity, and then there is spherical. There is some star can be have a mass m, okay, mass m. So Barkov theorem tells us that these two configuration cannot distinguish. Even like this star can be just move S move, like how do I say, expanded or contract by S move way. The metric is insensitive of this at the infinity. So the helpful. So here, so this configuration at the infinity you cannot distinguish. But here it clearly in this in the space integral clearly have a stress energy tensor inside. So you can just clearly have the energy. You can just have a non-trivial stress energy T00 component is inside here in the star. So therefore is that upshot is that you cannot really see what's happening in the bulk of the hypersurface. But if you compute the metric of at the boundary, we can really measure the corresponding energy even in the vacuum configuration. Since when you compute the structure metric, what we did is something like, what we did is that essentially what we did is that the 1 minus Rg over R dt square plus inverse of d R square plus whatever R square d omega. So this is the vacuum equation. It's this way. Rg is free to fix. Okay, Rg is some constant. But to determine Rg, what we did is what? What did we do to Rg? This is, we know, whatever, 2m, right? Rg is equal to 2m, right? If you restore G, you can have a G or like whatever, C, something like that. I don't remember how you restore C. But we fixed Rg equal to 2m. How do you fix this constant? Do you remember? So G00. So if you just look at the Einstein equation, G00 should behave like the gravitational potential is R over what was that? M, right? What was it? So you just go to R goes to infinity, and then the Einstein equation becomes like this way: d phi is equal to what was the Poisson equation? Poisson equation is something like R square over some number, right? M. Do you remember? I think I don't remember. I don't even remember. Yeah, the phi is the 2 pi, sorry. Yeah, 2 pi g rho. 2 pi g rho. Sorry, 4 pi g rho. Okay, 4 pi g rho. And then this part can be understood as how to say, G00. So H00. H00 part. So that's what we did. So when you go to R goes to infinity, we just compare with this gravitational potential and the metric G00 component to fix Rg, right? To Rg. Okay. So really what we need to measure this constant is you really need to go to phi infinity to fix this RG. So therefore, what we did is that here is also the same. So here you look at the metric at the infinity and they measure the quantity at the infinity and then compute this one, you can have energy. Even though it's a vacuum, for Schwarzschild case, we still have a non-zero answer if you look at the boundary metric. Since we cannot distinguish vacuum and this without with some stress, non-trivial stress energy tensor in spherical metric. So therefore, some metric knows what's the boundary should know about the energy, and that's how we define this RG coefficient in the previous time. So that's the answer to your question last time. And then, yeah. Yeah, so, yeah. I don't remember the details. So this pi should be, so G00 should behave like 1 minus, yeah, minus 1 minus 2 phi, this pi. And this phi is something like m over. So this is equal to m over r. Okay, has to m over r. So that's what we learned. I mean, when r goes to infinity. Okay. So that's what how we fix this RG. Equal RG. So therefore, the same philosophy we have to use. So we need to go to the phi infinity to determine mass. If you look, you need to look at the metric of the infinity to determine mass. And then I'm not going to go into detail, but if you use this formula and apply this again, this asymptotic behavior, and plug into here, what you get is exactly this one. Up to some coefficient is changed, but in fact this second term can be ignored. Second term can be ignored by this is the order of r to the 0. One can always take the coordinate order of 0, so that if you do the integral of this s infinity, you get a 4 pi r squared, but the 1 over r cube is they decay faster than the r squared. So 1 over r squared divided by r cube is 1 over r. So once you go to r goes to infinity, the second term vanishes. So that what's left is this term and this term. Okay, this term. And then if you do the computation of the Schwarzschild, exactly you will get the from using this one. And they assumed this metric behavior, you will get exactly the same ADM mass. So this is the upshot of the ADM mass. And then the reason why I just the last is that I also want to talk about the angular momentum. Angular momentum. Okay. Yeah. And then so maybe I should mention that so I don't have a time to explain that there's an important theorem that the positive energy theorem, by Sean and Yao, and also by Witten. So Sean and Yao will give you 79. I think the famous paper is 79, but the series of papers around this time by Sean and Yao. Even 79, they wrote 3 papers about positive energy theorem, but 81 they improved the proof and so on. But anyway, But evidence proof is 81. He used completely different. He used a spinner method, spinner. Unfortunately, I don't have a time to do that. So stated that the ADM energy in just erase energy is the non-zero, non-negative, negative. If you assume assumption is the asymptotically flat. And obey Einstein equation. And the so-called dominant energy condition. So dominant energy condition is something like a R, A, B, Na, and sigma Na, sigma B is non-zero, something like this. And A is again the orthonormal to the time-like killing. How to say? The orthonormal vector. Sigma is a radial orthonormal vector. Or maybe I should use R. Maybe. If you assume this one, this is non-negative, and then this is, and also 0 only when Minkowski space plus space. Okay. So that's the theorem, positive energy theorem. So non-negative means it can be 0, but it can be 0 only when the space-time is Minkowski. So that's the important theorem for one of the how to say achievement. One of the achievement actually this Sean Yao did. Fine, and the momentum really comes from the second term. So the, as I mentioned, so the ADM energy come from K minus K0 of the ds at the S infinity. It's coming from here. There's a part coming from here. It's coming from here. And for momentum, so it's a part coming from the following part, pi g, S infinity k ij minus q ij k, and then ni. What did I write the previously? And j, yeah, and I and dsj, yeah, like this one, dsj, okay, and then if you just take the so this is a momentum J is equal to this one, and if you take this one, it's to be phi part. So in other words, so this and phi is equal to dxi d phi, like this way. So here, maybe I should write down up. No, phi I maybe downstairs. If you take this one, you can just have the angular momentum. And in the case of car, one can just compute the this quantity, so if you just write down the, yeah, so if you write down the spherical coordinate, this will reduce these to as follows in the curve case, and the spherical coordinate it just reduces it like this way: 8 pi g k s infinity and then k r phi ds. Okay, so j is equal to r. So this j index is equal to r, because I mean, as I mentioned, so this s infinity, and the ds is essentially this integral. dsj is the j is really pointing outward, and I is really the phi integral. So therefore phi is this integral. The I is and I is like this way. So the I take the phi and the j take r and do the computation of this one, and you will get the you get this one, and you can just compute this one as follows, and then 3ma over 4 0 pi and sinh cube theta d theta, and then in fact this guy is equal to 3gm a sine square theta over r square. Okay, so therefore one can just do the integration like this way. So the measure, okay, so if you do that d phi integral, you get the 4 pi r square, right? 4 pi r square, and r square cancel this one. 4 pi cancel 8 pi, and somehow I don't know the normalization 4 here. But anyway, so and what's left is sine square and the sine times sine theta times d theta, and this will give you ma, and which is exactly the angular momentum of car spacetime. Okay, so that's how you compute the momentum at the phi infinity. So here momentum is coming from this extended curvature part, and the k is really coming from the d dA RA part, and then just compute the perturbation metric to get the ADM mass. Okay, I think 시즌 차부터 Okay, so that's the case. Yeah. So sorry about. I mean, today the competition is really hard. So I just write down the lecture note very carefully. So I mean, if you got confused, you can always go back to this lecture note. Yeah. And then next week I will talk about the black hole thermodynamics. Yeah, just if you have a question, just let me know.